Yeah, so first of all, I want to thank the organizer once again, even though other people have done it, for this wonderful workshop and conference that was been great so far. And also for the opportunity to present indeed the first results from these new simulations, which are very preliminary, as my simulation friends know. Large simulations take a long time to run, especially very velocity dependent. SIDM is incredibly slow. So, but first of all, some motivation of why we decided to do this simulation. So, as we've heard already from people, and we'll have tomorrow in the observational talks, we like to try to constrain warm dark matter and self-interacting dark matter, comparing predictions to observations. So, for instance, warm dark matter to strong gravitational lensing, Milky Way satellites or streams, or the population of the Lima alpha forest that can tell us about the clustering on small scales. And SIDM, as we know, is all about the density profiles, so cores or cusps in the case of core collapse, and so one can look at stuff like halo shapes, again, gravitational lensing, galaxies, or cluster or satellites in clusters, and dwarf galaxies. So what's the problem in this? I mean, it's all very nice, but we know that these are also scales that are heavily affected by the presence of baryons. And so it can be tricky to compare simulations to observations if the two things don't match. And it would also be nice to have a sample of simulation that we can use to compare alternative dark matter models to observation at multiple scales at the same time. So there's a lot of fantastic work done with many zoom-in simulation on dedicated scales that can allow us to look at very high resolution in galaxies and so on. But we wanted to tackle the problem from a slightly different perspective. And so this is the origin of the AIDA project. So this is a sister project of the illustrious TNG simulation. So what we're doing is simulating 3 cosmological boxes. So at 100, 50, and 25 megaparsec in size, with Arepo, so with the moving mesh code written by Volker Springer after Gadget, and including, so we're running the dark matter only versions of all these simulations and the full hydro simulations, including the TNG galaxy formation model. Unfortunately, this will not be at the highest resolution of TNG because this will be not feasible, but it's just the one below. So the resolution of the 50 megaparsec box will be the same that TNG 100 had in the flagship resolution. And what we'll do is that each of these boxes will be simulated in, well, CDM we have already in more than one warm dark matter and warm dark self-interacting dark matter. So this will give us the chance to see the same volume with different models, the same baryonic physics implemented, and also make mocks and look at the population of galaxies also in light of surveys and new observations that are coming along. So the maximum resolution that we'll be able to achieve is in the 25 megaparsec box. Of course, smaller, easier to reach higher resolution is something like 3 to 4 in 10 to the 5 solar masses. So it's not as great as some zoom-in simulation, but it's still pretty good. So I guess most people working in the simulation side and observation know, but since for our particle physics friends, so the illustrious TNG project was this project of cosmological simulation where they had 3 boxes, one much larger, or 300 megaparsec, that we're not going to do. And so it has been used in literally hundreds of papers. So the advantage of this is that the behavior of the galaxy formation model in cold dark matter is very well known. It has pros and cons, but at least we can use it as a baseline to see what happens when we change the dark matter scenario. And also, hopefully, the new boxes will allow us also to evaluate what we need to maybe recalibrate in the baryonic physics in case we change the dark matter enough that we see different properties of galaxies. So one reason why we decided to do this is that so in cold dark matter, there's a lot of simulations. So these you won't be able to see very well, but these are all cosmological simulations from a size of 20 megaparsec to 300 megaparsec. These are all hydro, or mostly hydro simulations. So the Eagle, Magneticum, TNG, Firebox projects that we heard about. And so these are all contain many, many galaxies. They have different prescriptions for galaxy formation. So in CDM, we've been able so far to really try to understand what happens when you change the parameters in galaxy formation and look at galaxy properties on many scales. And so we see stuff like this coming out of projects like the illustrious or illustrious TNG simulations. So many mock images of galaxies on multiple scales. In the alternative dark matter model, this is not really the case, so this plot might not be super up-to-date, but we have indeed many zoom-in simulations that, as I said, are great for specific problems. But when you look at cosmological volumes, this is volume against resolution, so for computational time reasons, resolution and volume anti-correlate. And so the alternative dark matter cosmological runs that were available at least until last year were the Bahamas SIDM, Eagle, Tango SIDM, which is one of the newest, and the TESAN volume. So not very many. So we want to try to populate the upper right part of this plot to have a larger statistic and better resolution. And so this is, of course, we can only do so much with like the computing time, which is already a lot that we got. But you know, if you want to run more than one model for each box, it gets tricky. So we'll try to get a bit more volume or a bit higher resolution than what is available. But most importantly, each of these boxes will be available in something like 6 variations of dark matter, while this is not the case. So most samples simulate either warm or self-interacting dark matter. So it's hard to then compare the same galaxies. Yeah, and just let me give you an example based on our work on why we think running large box simulation can be useful and can really be complementary to what we do with zooms. So a few years ago, we selected roughly 10 elliptical galaxies from the TNG boxes and re-simulated in zoom-ins, including self-interacting dark matter, very basic model with a cross-section of 1. And here they are shown in the stellar mass versus size relation. So it's the yellow and blue, light blue points, and all the other points are just other halos in the simulation. And this was to compare to the population of strong lenses, which are the stereotypical strong lens is an elliptical galaxies around ratio 0.2 or 0.5. And so we looked at their profile, and what we found, for instance, in this sample of 10 objects, is that there was a group of the very high mass end where they were really regular elliptical galaxies, where you have a core in SIDM as you expect, although the stellar mass was roughly the same and the stellar profile was roughly the same. So given that there's less dark matter at the center, the halo is a less efficient lens. And so when we simulate the strong lensing signal, the lensed images are smaller in SIDM than cold dark matter. So the Einstein radius is smaller. But then there was a second group of galaxies that were a bit lower masses, like 6, 8 in 10 to the 12. And in this case, the density profile in SIDM was steeper at the center than in cold dark matter. And so in this case, the size of the lens images is a bit bigger. And the combination of these two effects makes up for a weird change in the distribution of the Einstein radius if you think this is representative and try to simulate what you will see in a survey. And so we saw there was some correlation with the merging history, so that the highest mass will form later. We thought this can be due to the fact that the second type of galaxy, the galaxy formed much earlier, so it dominated the potential, which is probably still the case. But then these were 10 objects, and then my students also looked in the Eagle 50 SIDM box run by Andrew Robertson and selected halos around 10 to the 13, which in this case are like 100 objects, more or less. And so you can see that the profiles, so the stellar profiles are very similar. So the line made of stars is the stellar profile. And then also the total profiles, in this case, on average, are very similar. And so here is the distribution of the Einstein radii. So it's in arc seconds, so the size. And so the gray and light blue curves are the cold and self-interacting prediction. You can see there's a slight maybe shift, but not that big. The good thing is, on average, they're consistent with the dashed histograms, more or less, which are the Einstein radius of observed lenses from 2 samples, which is good. But in this case, we couldn't see so much of a difference. So the question is now how to compare the 2 results. So was it just that we had only 10 objects? Is it because this Eagle, different code, different baryonic physics, different prescriptions? Or is it just a matter of statistics? And so this was one of the reasons why we got inspired to run larger cosmological boxes to test dark matter models at multiple scales and with many objects at the same time. Yeah, so diving into the models that we have. So here on the left is a compilation of constraints from one of Irzi's papers. So it's mostly Lyman alpha constraints. So the top are some non-Lyman alpha. There's probably newer ones, but for gravitational imaging, Milky Way satellites, flux ratio, and stellar stream, the rest is Lyman alpha constraints. And these two lines are corresponding to 3 and 5 keV. So models warmer than 3 keV we know are more or less already ruled out. And so we'll try to run these two, so the 3 and 5 keV, so 5 keV only in the highest resolution box to see some difference. And instead, in the self-interacting domain, we'll have a constant cross-section of equal to 1 for now, just to compare with previous works, and velocity-dependent model, including the parametric fit from Camila Correa's paper, which is a velocity-dependent model that reproduces the fit to reproduce the property of Milky Way dwarf spheroidal. So the cross-section is around 100 at dwarf scales, and then it gets to 1 at galaxy scales, and then it's very low in clusters. And yes, so this is a table summarizing what we will have, hopefully. So a resolution of 10 to the 7, 10 to the 6, and 10 to the 5, and then also increasing spatial resolution. Not all boxes will be running all models, because in some cases it's not worth it, like the low resolution, if you run them at 5 keV, you don't see any difference, for instance. And not all the green points are actually finished, but they're in the making. But all the dark matter only runs are finished, all the 100 megaparsec runs are finished, most of the 50 megaparsec runs are finished. And so if we have then additional computing time, we might also run some inelastic, like the endothermic or exothermic model from Stephanie O'Neill papers. And who knows, if there's extra time, please tell me about your favorite model. Maybe there'll be time to do it. So if people are familiar with the TNG boxes, this will be equivalent to the 102 and 52 runs. And as I said, hopefully all this will tell us about how to change the hydro model. Do they work? Do they produce the same properties of galaxies or not? But so, okay, on to some first plots. So looking at the large scales, the obvious thing we started trying to measure is the mass function and the power spectrum to see what happens. So for the halo mass function, so now you will see, so here it will appear the dark matter only mass function and the ratio or alternative model to CDM. Then this is the same, always ratio, but in the hydro model, so just number respect to CDM, and this is instead each simulation compared to its own dark matter only counterpart. Of course, this plot will have more lines because all runs are finished, and here not so much. But so for the SIDM simulation, so in dark matter only, we see basically no difference. In the hydro run, there's this slight increase at the low mass, so there's slightly more halos than in cold dark matter. We'll have to see if this persists with higher resolution or if not. And then this is the ratio of hydro versus CDM. So there is a suppression in the number of halos due to the hydro physics, which seems very similar in all models. So it's down to 10, 20% depending on mass. So these are the SIDM models. So for now we have the constant cross-section and the Correa model, and then 2 warm dark matter models. So for the very big, for the biggest raw resolution, we also had 1 keV as a test. This is why you see it here, and then 3 keV. And you maybe can see, but there's all the different resolutions that line up we can use to test as convergence. So each box will have 3 different resolution levels, and we can see what happens. And also, in this case, one nice thing is that the baryonic suppression compared to dark matter only version is very, very similar. So although there's differences between cold and alternative dark matter, both in dark matter only and hydro, the baryon seems to have a very similar effect, at least statistically, as we'll see next. It's not really true if you look at individual objects. Yeah, then we can measure the power spectrum that many people also mentioned yesterday. And so here is just the total matter power spectrum in the hydro run, the dark matter only run, and also of different components in the hydro run separately, so stars, baryons, and gas, which just fits with what was measured by Volker in the TNG 300 simulation. And we know that the power spectrum evolved from high redshift being very close to linear theory, and then departing due to nonlinear evolution. And we also know that the baryons have an effect. So here it's really small, but the dashed line are the dark matter only case, and the solid lines are the total matter power spectrum in the hydro runs. So they're all a bit lower. And so if one plots the ratio, so in cold dark matter, the hydro versus dark matter only case, you get an increasing suppression, also due to baryons in the power spectrum. And so what then happens in the other model is this. So once again, at least statistically, at least with this combination of models, they're not exactly the same. So as a constant cross-section SIDM is a bit different, but more or less the behavior, the suppression due to baryons seems very similar in all models. However, if we look at them compared to the cold dark matter case, then one can start to see the differences, since you expect that all these models will also suppress the power spectrum compared to CDM. So this is what happens. So this is the dark matter only run in different colors. So you see, so from redshift 3, 1, and 0. So warm dark matter is already at the beginning very suppressed, and then it gets a bit less suppressed while self-interacting, given that inside here we're basically starting to see the effect inside the halos. Due to the core, self-interacting dark matter gets even more suppressed at low scales than warm dark matter. So this is in dark matter only case. Then we can look at the dark matter in the hydro run, which is here. And so it's qualitatively similar, I would say. You get maybe an enhancement of the suppression in at least some of the self-interacting dark matter, like this one. However, for some reason that we are not really sure yet about, but the velocity-dependent power spectrum increases. I mean, indeed, we see by first looking at some of the halos, more concentrated halos and subhalos, but I don't really have a statistic now. So this is the dark matter in the hydro, and it's all matter in the hydro. So once you look at the total matter power spectrum, you see a smaller difference compared to the dark matter, again, because the baryonic physics pushes things to be more similar. Yeah, so these were some preliminary statistical plots. Then we can also look at individual objects, such as this. This is the biggest cluster in the simulation, and we can look at how the map changes for different models, which I'm not going to show because it's really hard to see by eye. Because these are not warm enough that you can really appreciate by eye the difference. But we can see that there's less substructures. For instance, this is just a cumulative distribution of substructure as a function of radius, and again, the ratio to cold dark matter. So warm dark matter has really many less, but also self-interacting has a suppression towards the center, at least in this case. And we can look at halo profiles in SIDM. So these are the stars of these clusters, which are remarkably similar. And then the dashed line are the profile in the dark matter only version of the simulation. So you get a core. Even in the velocity-dependent model, which has a very low cross-sectionality scale, there is some kind of a core, which then is washed out, in this case, in the hydro version, in the dark matter, but in the velocity-dependent SIDM, but not really in the constant cross-section SIDM. And finally, and so we see these are profiles in different beams in mass, from clusters to 10 to the 11 solar masses. And indeed, we see cores in the dark matter only profile. This is not the total profile, this is the dark matter only profile, especially at low masses. And then at big masses and at low masses, we still don't know. We have to check the resolution if this slight increase that we see in the SIDM models is real or not. And so then one last fun thing that I don't really have an explanation for yet, but I'm just starting to look at galaxies. So if you take, for instance, one Milky Way mass galaxy, and this is just the gas density, so it's nothing fancy, not division between cold and hot gas, just a projection in the gas density. This is how it looks in cold dark matter. This is how it looks in the Correa velocity-dependent model, so you still see same shape, but it's way more diffuse. And this is how it looks in the constant cross-section SIDM. So we'll see what happens. For some reason, it also looks different in warm dark matter. Unclear why. So this is one object. So it's just a nice example. I'm not sure what's the statistical significance of this, but it shows that these boxes could really give us a big sample to look at. And so just one final point that I want to advertise, that Thales Kutke, which is at the University of Hawaii, so maybe some people are familiar with the Lyra simulation, so these are dwarf galaxy simulations that aim to resolve individual stars, has also started to run SIDM version of one, at least, of her dwarfs, so it's a 9 × 10⁹ solar masses with a very velocity-dependent cross-section. And even here we see differences in the H1 gas density and the stellar surface density. This is all very much ongoing, so I'm not sure what will come out of it, but stay tuned for the results. And so just leave my summary.